Good afternoon, it's Mark and Bryant, and we're going to discuss our Moose project. To get started, we followed the tutorials provided by Moose so that we could learn how Moose works and then apply that to a custom change for an application that we could see ourselves using in the future.
For the first tutorial, and we just wanted to note that we weren't able to get Peacock to work, and so we ended up using ParaView to visualize the Moose solutions. So for the first tutorial, step one, we modeled pressure in a material sample, as you can see on the left. And the lessons that we learned from this were that the input files are used in Moose to perform simulations. Also, some of the items that input files require, some sections are mesh, variables, kernels, boundary conditions, executioner, and outputs. And you can change the numerical values in input files to change solution and solve for different conditions. You can also add different variables as well. And finally, you have to create an OPT file in order for Moose to run and visualize the input file, visualize the solution from the input file.
In step two, we were looking at pressure, and to do the rendering that we did, we had to learn about two types of objects. There's a kernel object, which allows us to use Darcy equations, which is basically just fancy math. And then the Moose object, which allows us to use our interface with Peacock, which, again, as Brian said, we're not using because we couldn't get to work. But if we could, we would be rendering this in Peacock instead. The meshes, as said, are required for either objects and allow us to do the calculations so that we can have this rendering. In step three, we added permeability as an additional property, and we learned about properties that can vary with time and space. These are done with material systems, which are a type of object, just like our other objects. And the reason this is important is because our Darcy-based objects cannot vary properties based on time and space. So our material system will produce the properties with respect to time and space, feed it to Moose, and then Moose can then look at current and old states, produce the new information, and plot it as we see here. It can also use functions if that complexity is necessary, and if there is a piece that is usually constant, then you can have defaults. Otherwise, if there's something that you definitely don't want the user to forget, then you cannot have defaults and require them to put it in so that Moose will run your system. In step four, we included velocity because although velocity is not a property, it is a mechanic that is related to some things such as pressure that might be changing, such as the fact that we were solving pressure earlier and it does change. So this uses an auxiliary system where we have our mesh and we can have these mechanical, not properties, but the mechanical things such as velocity solved by looking at the elements in our mesh or nodes between the grids in our mesh, field variables, pretty much anything that would allow us or where we'd want to use a non-linear use case where things are changing, and we can solve for it almost kind of like an iterative sense where it's looking at these pieces and it's cutting it up and solving it as a finite element. In step five, we now are looking back at temperature. This plot here is the temperature at the initial timestamp. That's why there's no gradient here, but we could have done it with respect to time if we wanted to. As part of this tutorial, we learned about heat conduction. So we have a couple types. It can be constant, it can be time dependent. We cannot make it space dependent, but if it is dependent on something, then we can have an iterative process where it calculates over, say, time, which is the most likely scenario of what the new conduction coefficient is, or whatever their application is. There is going to be an error because it is iterative if we're not integrating. And based on our iterative processes, Moose will actually give us an error output so that we can know by what off amount we could be. But we do have the opportunity to integrate even over boundary conditions. The default is that there is no boundary condition, so it's a heat sink. But if needed, we could add that to our conditions.
In step 6, we took it a little bit further and not only analyzed temperature, but also viscosity. The lessons we learned from this tutorial were that in pair view, you can plot values on a graph and press play to have it show the changes over time. And so you can see how the temperature and viscosity changes with respect to time for each time step. And you can also automatically scale non-linear variables in Moose to obtain a better solution. On the left shows the results of this tutorial, temperature and viscosity plots throughout the material sample. In step 7, we also were able to plot the graph at a specific time step. As you can see on the left, we plotted at 14.8 seconds. We plotted the temperature, and you can see the response in the graph there. So what we learned from that was that you can refine or coarsen the mesh in certain areas automatically using H adaptivity. And in order to do that, you need indicator objects and marker objects. Indicator objects measure error, and marker objects mark where to refine or coarsen the mesh based on the indicator measurement. And so those both go in the input file and can help you refine or coarsen the mesh. And Moose also has built-in markers and indicators, such as error fraction marker and gradient jump indicator, to make it a little easier to use markers and indicators to refine the mesh.
In step 8, we have we're slightly more complicated data. We have temperature gradient that not only differs with respect to time, but also where we are in our element. And as we get more complicated, we can expect that we're going to have really complicated graphs sometimes. And so it's important to be able to aggregate. So tutorial step 8 talks a lot about aggregation. There are, if we think about our mesh again, there are elements, nodes, boundaries, interfaces, and internal sides in our mesh. And if we wanted to aggregate any data with respect to any of those, we can get either a scalar value, such as the total maximum or maybe the average across the whole thing of some information, or we can get a vector of data, such as if you want to do the averages, but for every timestamp or something like that. As long as you are not doing an interface, you can get a vector of any amount of data that you would like to know about. In step 9, it's starting to get more complex. And as you can imagine, for niche or specific scenarios, you might want more niche or specific types of things that you can do. And those might not be in your normal base use cases. So maybe you have chemical reactions. Maybe you have fluid properties like density or enthalpy. Maybe you care about porous flow or for some reason need discontinuities. You can do all of those things as long as you have the right module that you're using. In our example here on the left, we were looking at strain and solved for von Mises stress with respect to some temperature. And although this isn't as complex as it could get, this is showing the need for these modules that you can use for more specific cases. Now that we have learned about how to use Muse, our application is to look in a nuclear reactor with a UO2 fuel cell, and we can measure temperature and von Mises stress in our sample by changing some factors inside of our input files.
The first modification we chose to do was to change the thermal conductivity based on burnup and temperature. And so on the left shows the input file that we edited and where we edited the thermal conductivity to the values that we solved for using the equation on the right, equation 2.18. And in that equation, we were able to input temperature as a constant temperature, and burnup we varied in order to get different thermal conductivity values. The results shown here on the left is an image of the material sample, the UO2 sample, the temperature profile throughout it. And the fundamental behavior we observed was that there were heating and swells over time. And the material properties that the notes on material properties that we noted were that it became less thermally conductive as burnup is increased. And also the temperature profile throughout wasn't significantly affected by changes in burnup. And changes in burnup also created changes in thermal conductivity via the equation in the previous slide. And so as we have evaluated the burnup, as we varied the burnup between 20, 30, and 40 gigawatt days per MPU, which was a reasonable amount, the thermal conductivity didn't change by very much, and that caused the resulting plot to not be affected very much either. The temperature wasn't affected very much. And also the von Mises stress similarly wasn't affected very much by changes in thermal conductivity. The fundamental behavior we observed was similar, that there were heats and swells over time, as well as stress concentrations in certain areas where dislocations may have built up.
Our second modification was to change the thermal expansion coefficient based on the temperature. To the right, we have our equation we used, which we use more than once, and we are able to put right here on the left for the thermal expansion coefficient in this little module, and we will be able to see what happens. There were several data points, so we have several images that we'll show on the next slide, and but it was very busy. So here, I'm just going to discuss the fundamentals and material properties. Again, we saw some heating and swelling over time, but we did notice that as the coefficient of thermal expansion increases, the temperature and von Mises stress throughout the sample decreases. So on the next slide, you will see evaluated at thermal expansions, the values 0.05, 0.1, and 0.15 centimeters. Here we have on the left to the right, our coefficients of thermal expansion from smaller to greater. And we can see as it gets larger, the temperature is reduced as well as the von Mises stress, which is what we discussed in the previous slide. And that is our project.